Well, it's time. Welcome back, everyone. We're about to close out week three. And so the big announcement for the day, of course, it's kind of a repeat from Tuesday, is that we're coming up against into our first exam. It's only going to cover these three sections, like we mentioned before. And we're about to finish off the section 2.4 today. And I'm learning to grade in Canvas for the very first time. So let me know if you have any issues on receiving your section 2.2. I pretty much just put it into Canvas as a graded copy of a PDF for what I marked up on your paper. And I'll be doing the same for section 2.3. I should have that graded probably about the very first thing on Friday. And I'll be working as fast as possible on grading the 2.4 as well. But any questions or comments at all today, folks, to start us out? Okay, as far as 2.4 goes, the due date is going to be February 5th. I pushed that over just today, a few minutes ago, after logging into Canvas, only because I'm going to maintain that pattern of the day we finish this section gives a 1 week turnaround on the due date. But as far as these due dates go, just to reiterate comments we've been making along through the course, the due dates are just for the sake of pacing. It's a date at which I'll put in a grade if you have the assignments graded. If you didn't have it turned in just yet, you would get a 0 for the moment. So if you're just a little behind on, say, section 2.3 today, but you get it into me on Friday, that's when I'm going to be grading it anyways, you'll still get full credit for that. I don't have a late policy. There's no late penalty or anything like that. And for 2.4, the due date is a little bit awkward. It's on Thursday after the exam, but I've mentioned before, probably the best thing you can do to prepare for exam one is to just be fully caught up on these particular three sections. So if you decide to do this as part of your exams preparation, that'd probably be the most optimal route for studying. If you finish it off, say Friday, Saturday, or even Sunday, and turn it into me, I'll make every effort to grade this early and get it sent back into you. Typically, I like to grade these when I have the full set. When it's past the due date, it's just more efficient for me. But when we're coming into an exam and there's a last section hanging on like this one, I'll try to get these graded early so you can get that feedback early to help you prepare. All the comments are make sure to schedule your exam one as soon as possible with either the Pocatello Testing Center or the Idaho Falls Testing Center, or otherwise if you're in a far further remote campus. If you haven't seen those instructions come in through Canvas or Gmail, give me an email right away and I'll send you the link for scheduling your exam. But I think that's pretty much the roundup for the announcement of exam one, kind of just reiterating from Tuesday's class. Also, this is going to be the last page of the real exam one, the formula sheet. And these are some sample example problems that you could look into for further practice once you're fully caught up with the homework. Well, any last questions at all, folks, about the upcoming exam one, or any questions at all otherwise? Okay, well, let's delve back into our current work. We're finishing off section 2.4. Our schedule is pretty tight. We don't have redue days before exams, but that's one of the reasons why I try to make our exams pretty parallel to what you're actually doing in the homework, what we actually do in the lecture notes, so that I'm not going well beyond the material because we don't have a review day to say, well, what else could happen on an exam, for example. If you're getting through these homework sections carefully, you'll see the same type of problems at the same difficulty level on the real exam. But we were nearly done with section 2.4. I'm glad we didn't quite finish it off because we left off on maybe the computationally more intense topic, matrix multiplication. So let's review this. We'll practice a few problems and then move into section 2.5. Well, there's a lot going on here. So let's maybe start here on the definition of matrix multiplication. We're related to the first entry we found, 9, on the product, which is of size 3 by 2. But the notation is, again, one of the major challenges with matrix multiplication. So let's rewrite this here. If we say A, IK, B, KJ, or hang on, let me highlight the correct thing that's changing. As the index K changes, this gives us an entry, MIJ. This entry right here would have been M 1, 1. That's a good idea to put a comma there so it doesn't look like the number 11. So this is the entry in the multiplication of A times C that ends up in row 1 and column 1. So when we see the I here, we're thinking row I. Okay, here's saying row K. But notice that means over here in this indexing, that's going to be row K, and that J will be column J. So to build out all the entries, if we're in the ijth entry, somewhere inside this product of A times C, what it says is the thing that's going to be varying is K. Will stay on a row, but if K moves, excuse me, let me double check that. As K moves, it's not the row that changes, it'll be the column. Sorry for that error right there. It's good to keep these straight, rows versus columns. Yeah, good eye, Sophia. Thanks for catching that as well. I looked over here and I saw the chat pop up, so I knew something wasn't quite right. Thanks for spotting that. So let's start off again. If we're looking into the ij entry, the index K moves, but the row is frozen here and the column is frozen here in B. So we move across a particular row because we're changing the column entry, move across the row in A. And that's why you see this yellow highlighting here. We built out that first entry and we're just varying which column we're in, moving across the row. Here, we stay fixed on a particular column, J. So that's column 1 that we stayed fixed on. We didn't move that column, but the row changes. That means we're going down along the column. But in the end of the day, you can almost imagine this as kind of a dynamic picture where the entries here along the row kind of move over and they line up with the entries here on the column. You multiply them pairwise in this way. That's what the product here is indicating. You sum them all together. So there's the sum, the pluses, and you get your entry. Then if you want to get the next entry, say in the same column, you just change I to I plus 1. On paper, this is what it looked like. We're changing to just that new row, do the same kind of multiplications, and it'll build out an entry right there. Okay, let's run through this in full to see how it goes. We'll practice a couple additional ones just to get a good feel for matrix multiplication. But any questions so far, just looking into this core definition? Okay, the major and key insight is this is really just a dot product. It looks fancy when you write this out, and it has to be written out exactly this way to say literally verbatim exactly what we mean. We have to say what we mean and mean exactly what we say. So it gets messy when we're trying to be precise. But if you visualize this as a dot product, you'd be taking 1 plus 1, so we're at a 1, plus 5 times 3 for a 15, so we're up to a 16, plus 0 times 0. The entire dot product of those highlighted rows would then just be 16. Then we vary, we push this down, go to that next row here, stay frozen on this column, and that means that the entry we're trying to build out next, that didn't work, is just down below that 16. Uh-oh, hang on, having some Microsoft Word struggles here. Okay, that's working out. To get that entry, just a new dot product, these numbers times these numbers. So if we did that dot product, we would have 3 plus 6, so we're up to 9, plus 7 times 0 for a 0, so it totals up to 9 exactly. And we did it, folks. We built out the entire first column here. Now we're just going to go for the next column. But any questions at all getting those entries, 9, 16, 9? Okay, going on to the next column. Here's the idea. We're going to vary our value J. J is going to move on to a 2 on this one, which means we're building out column 2. Here we start off with our I value being a 1 again, so we're going to start into row 1. That's because we're going for this entry, the 2, 1 entry now. So thinking in terms of the dot product, we'll have multiply the corresponding elements in blue, 0 plus 3 minus 4. So this is just a 3 minus 4 for a -1 value. Then it's rinse and repeat. This is really just kind of a pattern that you want to practice with one finger essentially moving this way, the other finger moving that way if you're doing this on paper. Multiply the corresponding values. You can write out the values like this if you like, particularly if the numbers get nasty. But if they're kind of well contained, like in this problem, usually what people do is just think mentally, this is 1 times 1 for a 1, plus 5 times 1, so the total is now 6, plus 0 times 1, so we stay at that total of 6 altogether. So we have the entry 6 here, forgot to highlight. So multiplying this dot product with this gave us that entry 6, and one last one to go. Let me know if my numbers go sideways. This is a lot of arithmetic. And by the way, if you were doing this as an exam question, and I can tell you know what matrix multiplication looks like because you essentially have everything here, but maybe one of the numbers is off, you probably won't lose points. I would say you get the concept of matrix multiplication. You might have just had a small hiccup on the arithmetic side. If a few of the entries are off, then we start losing points on here, but I'll be grading these on partial credit. So last one is going to be, the ones are kind of nice. It's going to be boiling down to 3 plus 2 plus 7. So altogether, this will be a 12. Well, we did it, folks. That's the entire landscape of matrix multiplication. Any questions or comments so far with this practice problem? Okay, so just for the sake of getting more practice on this, here's a few more or a couple more problems. This one says take C times B, and it's always good to start here, the analysis of the size of the matrices, to see if the dimensions actually match up for this. Looking into the matrix C, C is of size, let me get a different color pen. It has 3 rows, 2 columns going this way, so we'll call this a 3 by 2 matrix. So 3 by 2 for the matrix C. The matrix B is of size 3 by 3. The person on the iPhone, sorry, I don't quite know the name, says, what is the level of work here where it's supposed to show for the exam? I'm using to having tests where a lot of computations are just implied. I would say if you did A times C and just showed me this, that would be a sufficient amount of work for this kind of problem. Were you thinking a different question or as well, or just mainly this one here?
Just kind of overall, because for assignment 2.2, we were doing things like logarithms and exponents, and it's like, I'm in high level calculus. It's just assumed that you know that.
Yeah, exactly. I would say as far as the exam goes, let me take another look at that question with you or that section just to give some good advice. So 2.2, maybe some of the most generic advice ever is if you can do a computation just in your head, then I wouldn't require you to put that down on paper. And only exceptions would be anything that has to go along these lines. Say, for example, if you just know that the floor of E is 2, I'd be completely fine with that. For this one, if you just know that this works out to 1/9, I'd be okay with that as well. But you might want to actually show a step or two in the middle for just the sake of partial credit. If there was any small mistake and I don't see the middle steps, I might lose basis for partial credit. But if you just see it and you know that's exactly 1/9, then I'm okay with that. And there's one I'm looking for specifically. If I ever ask, say, a question where I want to see the logic of how it comes together, just to emphasize, say, in this problem, the exponential laws, I would always say this very directly on the exam, show all the steps, do it by hand. But this one for us was mainly kind of a practice problem, getting used to exponent laws as a review. We did the same kind of instructions on the homework, but this would be a less typical thing you'd see in an actual exam setting. Let me see if I have other examples to think about. As far as the logarithms go, if you just said, say, 5 on this, then that's completely fine. I would assume you're well versed in logarithms. Again, if you're off on that number, but you had a check here, that would be weird because the check has to reveal that something is wrong. But anything additional that you show me on paper could be worth partial credit if the direct number is a little bit off. And same for the modulus, just stating 2 here, 5 here. And this one, if you just gave me 2, I'd be okay with that. I would think maybe you're thinking in these kinds of terms, but ones with a negative value are kind of sketchy. Just to make sure that nothing weird goes wrong to collect any possible partial credits as insurance on the problem, steps is probably a good idea, say, on these kinds of problems here. But does that help out with the advice on level of work to show in an exam setting?
Yes, thank you.
Yeah, absolutely. Other questions about that so far or otherwise? Okay. And by the way, let's suppose this is a real exam question right here. If you did A times C, and I like to put this on paper just for my own mind, so I'm not having my eyeballs jump from one thing to the next. Sometimes I'm more precise if they're just right next to each other. But if you're doing this problem here, it says evaluate if the expression, excuse me, evaluate each of the following. If an expression is undefined, say so and explain why. What would you all say for this particular problem?
It's undefined because the inner values don't match.
Yeah, absolutely. I should kind of reveal the notes to kind of indicate that. Those values here and here have to be equal, just as you said, for matrix multiplication. So if this was a real exam question and you wrote down something like this, let's make it look more official so it doesn't look like just a sideways comment on the notes. If you wrote 3 by 2 against a matrix that's 3 by 3, and then just emphasize that this is a mismatch, so undefined, then I would say you hit the instructions on that just fine. You said it's undefined, you explained why this does it for me. If you just circled these and said undefined, you're really conveying that to me as well. Or some people might say the number of columns in the matrix C is not equal to the number of rows in the matrix B, therefore undefined. That's fine too. If you feel like being a little bit wordier, if you have the extra time on the exam, that's no harm done. But this really just gets right to the heart of it. We can only do the matrix multiplication if the inner values match. As soon as they're off, we say undefined and we just move on to the next. Which means these kind of problems are sort of nice in a way. They're a freebie in a certain sense. Any questions with part B? Okay, let's try this out again. Part C says we're taking the product of the matrix B times 3 times the identity matrix, so the identity matrix scaled. The identity matrix is a 3 by 3 one, so if we did the dimension analysis on B, that's 3 by 3. The identity matrix, even if you scale it with 3, still a 3 by 3 matrix no matter what you do. So this one is defined. This one's a little bit different in a certain sense. There's lots of ways to solve this one. Here's one idea you could take. B times the matrix 3 times I. We have a bit of a nice commutative algebraic property when it comes to a scalar multiplying there. That scalar can be put just completely in front, and then you can take the matrix B times the matrix I. And I being the identity matrix is really extra special in matrix multiplication. You can verify this, that it turns out multiplying, let me be specific on the kind of multiplication, post multiplying by I is analogous to multiplying by 1 for numbers, or we could call them scalars, in R. So I is much like the ordinary number 1. This is much like saying take 5 times 1, you get just 5. So that's kind of a nice matrix in a certain sense. That means that this just boils down to 3 times b, since we were multiplying by the identity matrix. If we're doing 3 times b, all we're doing is scaling that matrix. Every entry gets tripled. So the entire punchline to this one is 3, 0, -6, 15, 12, 9, 33, -9, 0. And we're done right at that step. If you did take 3 times I, you just have this element, or this matrix rather. This would come out as a 3, 0, 0, 0, 3, 0, and 0, 0, 3. And then finally multiplying this matrix B by this scaled identity matrix, it produces the same exact value. It's much faster to do it this way, but if you did the ordinary matrix multiplication, you would get the same result, just more mental arithmetic that you would be potentially doing. I feel like we should do one more, maybe A times B, just to round out this section. But any questions at all, folks, with part C? Okay,
This
let's go to
might
that. Go ahead.
this might be asking a little too much, but could we show the difference between A times B and B times A?
Yeah, absolutely. That's a great idea. I think we made a comment somewhere here. Let me double check. I think it was a verbal comment. So let's do that and then throw the comment here on paper so it's not just something we said at some point in class. So here are those matrices just for quick reference. And here's the thing that kind of goes wrong in the landscape of matrix multiplication. We can say in general, A times B is not the same as B times A. What we mean by that is for the right matrices, they could be equal. We're not saying it's impossible, but if you grab just random matrices, and I have essentially done that here, we can almost guarantee we can't expect this to be equal. They're probably different. And I haven't done that product. I think I've done A times B, but I haven't done B times A. So let's see just what happens on that. And that's definitely not too much to ask, especially for a problem like this, where this is the last section that's going to come onto exam one. And I think it's, again, a pretty good computational exercise practicing these kind of products. So if we take A times B, these are both of size 3 by 3. And so we know the product is guaranteed to be defined, and that the result will also be 3 by 3. So let's do this multiplication going this way. I'll use the highlighter to kind of indicate where we're multiplying, the entry we're building. I'm going to start by building out a column. So this column is frozen. We're going to pretend like these don't exist at all, the column 2, column 3. And the row is just going to go down as we work through the product. The moment we're just taking dot products. So kind of like the zeros we see here, this should speed line it to just a little bit. Imagine in your mind that these 3 numbers kind of become lined up with these 3. You pair them off, multiply the corresponding elements, and then sum them together, all the products. We'll have 0 to start, plus 0, plus 8. So there's our first entry there. Then, going down the line, again, let me know if my arithmetic goes sideways at any point. I'll have 1 plus 0 plus 0. So not so bad so far. Last entry, we have 3 plus 0 minus 14. So looks like a -11 on that entry. And at that stage, we are done with column 1, and we just vary the column, work on column 2 to build out the second column here. It's now rinse and repeat. Start on row 1. 3 more dot products are going to be 9 in total. Before we get to the next column, any questions or comments whatsoever getting those 3 entries?
What is that first number in the first row and column?
That was at 8. Let me fix that.
Okay, thank you.
Penmanship there. You bet. Thanks for asking about that. Other questions so far? Okay, let's work these out. I'll just put one big yellow highlighting here. The yellow highlighting here is going to go down, and we'll pair off the corresponding elements, multiply. So it's 0 plus 12 minus 12, so 0 in the sum total of that one. Drop our focus to this entry. And next it's going to be 5 plus 20. So I'm up to 25 plus 0, 25 in total. Numbers are getting kind of out of control, it feels like. So if you ever feel like these numbers are getting a little bit rough, don't forget that. It's an open scientific calculator exam, so no harm, no judgment whatsoever if you're a little bit worried about the numbers getting large. So here, just to make sure I'm accurate, this is going to be 3 times 5 plus 2 times 4 plus 7 times 3. So we get a 44 altogether. And it's kind of nice just to see this a couple times, just to see the correspondence on how we're getting those entries. So 44 on that entry. And then back to the rinse and repeat phase. Change the focus to column 3 and vary across the rows, taking the dot products. This one will be 0 minus 9 plus 0. So -9 on that entry. And then down below, 150, that's going to give us 11 minus 15, so I'm at a -4, plus 0. And then last dot product, 33 minus 6, so I'm going to be at a 27, plus 0. Okay, as long as I didn't mess up the arithmetic at any stage, my claim is this is A times B. Certainly is defined. I'll erase this part right here so it's not too much of a visual distraction. If the matrices are both square of the same size, they're automatically defined. Next, we'll take on B times A. But as far as B times A goes, I don't think I'd want to have this on paper and just look at this as I run through it. The mental pattern of how I put these together, at least in my own mind, really depends on seeing B come first. So I think this is a good one to take the time and just rewrite it for the sake of accuracy. 1, 0, -2, 5, 4, 3. 11, -3, 0 is the matrix B. Multiply against A, 0, 1, 3, 3, 5, 2. -4, 0, 7. It's good to double check these values. Imagine if you're doing this as a homework question, it's easy to miscopy something. Okay, I think we've got the right values. Now let's focus on working this one through. Using the same pattern of attack, we'll build out this column by just really fixating on that one and varying the rows on the matrix B. So let's pair these off, multiply. I have 0 plus 5 plus 33. So that comes out as a 38. Let me double check my numbers. That for some reason feels weird. Yeah, it looks like a 38 on that. And already these are unequal. Matrix equality insists that every corresponding entry is exactly equal to every other corresponding entry. So just from those two values right here, we have discovered that A times B is in fact not equal to B times A. So another way to say this is, that's a comma, matrix multiplication is non-commutative. Commuting meaning moving entries around when you have a product like this is what would mean to commute. 5 times 3 is the same as 3 times 5, but not in the landscape of matrix multiplication. So the algebra is pretty weird on these kinds of things. But finishing this off, just for the sake of the practice on it, here's the next run. We'll have 0 plus 4 minus 9, so this will be a -5 altogether. Then next run, here we have 0 plus 3 plus 0, so 3 altogether. Again, you kind of have to love those strategically placed zeros on this one. It's kind of helping us out. We built out the first column. Now we just do the same thing with column 2. Starting with row 1 and moving it down the line. Any questions at all, folks, on building this so far? Okay, let's run through it. So again, the big punchline is you just know which row, which column you're dealing with. You're taking the dot product of those particular entries, and we'll get here 3 plus a 25, so I'm at a 28, plus 22, so 28 and 22, I believe I'm at a 60. Let me know if my numbers go sideways. Like that's a good one to double check. Okay, so moving on to the next entry, 0, 4, -3. I've got a 0, a 20, minus 6. So that'll be a 14 altogether. And last element of this second column, -6 plus a 15. So I'm at a balance of 9 plus 0. So 9 altogether.
I think the first one might be 50, but I also might be wrong.
Let me double check that. I'm going to believe you on that one. Let me pull up the calculator for this. Again, the calculator is not a bad idea to show on screen anyway. It's just to emphasize the way this all comes together. So I'm double checking this row against that column in blue. And this would give us 1 times 3 plus 5 times 5 plus 11 times 2. And yes, you're absolutely right. That comes out as a 50. Good eye on that. Thanks for spotting that one, Sophia. So 50 on this entry after being extremely careful on this. Again, don't forget, you're allowed to bring a calculator, and testing centers can run out of them. They're not able to necessarily offer everyone a calculator, so don't forget yours. And the correction on this one is it should have been a 50 here. Now imagine this is a real exam question on exam 1, and you've got everything right except that one number. I would just look at how you got through this and tell myself, yeah, this person knows matrix multiplication. If there's one error like that, I don't think I would take off a point. I probably just make a comment on paper. There's a small mistake there. I'm thinking of grading in terms of partial credits, emphasizing the concept overall. So if there's a bunch of errors like 2, 3, 4, 5, that's when you might start losing some points in partial credit. Well, we've got the second column down. It's the same game, third time, focus on this column, building out to that third column here and the resulting product. Okay, let me know if I lose my head on the arithmetic again. So I've got -4 plus 0 plus 77. So 77 minus 4 should give me a 73. Then next run, this will be 0 plus 0 minus a 21. Finally, the zeros are helping out a little bit. And final dot product. This will be +8 plus 0 plus 0. So 8 altogether. And we've got it, folks. That's A times B, B times A. That was a good problem to take a look into just to emphasize that major concept, but also good practice to see how this really all connects together. When you practice this a few times, it just feels like kind of an automatic process after a while. Any questions at all, folks, on running through any of these? Okay, well, we did it, folks. This is the extent of the exam 1 material. I'm not going to try to write a huge exam where you're writing down stuff as fast as possible for an entire 75 minutes. So that means I can't ask every single question that came up on the notes. It's going to be a representative sample of the major topics. I do believe I did put a matrix multiplication down on paper, so this was a great suggestion to practice this one here. Let me save this up. And next, we're going to take a look into kind of a fun section, 2.5 on functions. So here's the next section. The landscape of what we even mean by a function is a pretty vast landscape. the world of functions have so much interesting chaotic structure going on that really we can't say too much on these notes or we'd be stuck in this section all semester. But there's lots of great things we could start with just as a roundup of how you define functions, thinking about their domain, codomains, and the major interesting properties of one-to-one functions, onto functions, and the so-called bijection functions. So those are going to be the major concepts of these section notes. And here's the definition our author provides for a function. Let's run through this to see what's going on. The concept of a function, again, is one of those interesting concepts where everyone kind of intuitively knows what a function really is. For example, when I grade this course, I have a function. It's a mapping that goes from a domain, A, all the students, to a codomain, the set of real numbers between 0 and 100, where I just give you a percentage. Or maybe you're thinking of your grade as a letter grade, that's a different codomain, where it's the various letter grades like A, B, C, and so on. So that's a one-to-one mapping because if you're a student in set A, the domain, not a one, yeah, it would be a one-to-one mapping. You expect that every student gets one and a unique grade altogether in the domain here. So we're just kind of putting down on paper some of these intuitive ideas that we see all the time, like say assigning grades to students and so on. To start off, we have to have non-empty sets. So the domain, the codomain have to be something. We'll say a function that goes from A to B can be indicated this way by shorthand. It'll be f indicating whatever the function is, whatever name we give it. It could be generically f, it could be p if it's a population function, or maybe p if it's a probability set function. I'll go from A to B, where A is the domain of that function, and let me vary the color coding here. B is the codomain of the function. The idea is each input value, that's value from the domain, will have some unique output value. That's a value B in the codomain. Assign it away so that B is assigned to A, and we denote it by f of A. So in other words, we'll just say f of A outputs the B in this particular function, whatever it happens to be. Again, we've studied functions for quite a lot. Some people think of functions as some kind of curve on a graph that passes a horizontal line test. This is a nice standard definition of a function here. Any questions about it so far? Okay, this is the definition that our author gives, so that's why it's here in the notes. But I kind of wish the author also gave another kind of definition as well, or maybe mentioned it. There's a really cool connection between what we mean by a cross product in just the last section, notes 2.4, and what a function really is at the very same time. There's a cross product that's being indicated here out of nowhere, which is sometimes easy to miss. So here's an alternative definition for the sole purpose of just connecting the dots between the prior section and this one. A function, let's give it a name f, just like in the notation. It'll map from A to B. So A is the domain, B is the codomain, is a subset. Let's call it a G for the name of that subset. It's a subset G of this set, A Cartesian cross product with B. This is a good problem just for the sake of review. A cross B is the set. We used angle brackets before, but in this context of a function, I'll go with the more familiar parentheses, as in an ordered pair. This is going to be a set of ordered pairs, A comma B. Such that A is an element in A. The second component, B, is an element of the codomain, the set B. So a function is nothing but a subset of this cross product that we studied in the prior section. It has to have a property, and that property deals with the uniqueness here. This is the major part of a function. This is essentially, say, for example, the vertical line test in action. It's a subset G of the cross product with the property that if AB and actually, let's put a subscript on that. I think that will look a little bit nicer. A and B1 and the same element A with B2 are in G. Again, that's the subset of the cross product. Then the uniqueness property we see here in this definition our author gave insists that these values B1, B2, these are the outputs of the function. They must be the same. Then B1 must be equal to B2. So any subset with that particular property defines a function. If you change the elements in that subset, you've changed the function. And also, if you've changed the domain, you've changed the function as well. So there's lots going on with this. And we use G as a great way to indicate this subset because it reminds us, if you're looking at things like these, and maybe these are real numbers for the first component and the second component, all G really is the graph of the function. But when we say graph, we don't always mean something that can go on graphing paper because once again, this entire definition, as well as the one down below, also works if the domain is every student in this class and the codomain is a number between 0 and 100, or possibly a letter grade. We still call G a graph, and it still has this particular property. If one student gets a grade B1 and the same student gets a grade B2, that had better be the same grade, right? Or we're going to be dealing with the registrar quite a while to get that corrected. So that's a couple different ways to think about a function. Any questions or comments at the moment? Okay, when we deal with functions, in particular, say we're in algebra, calculus class, and so on, we get pretty fluent with dealing with the function notation that we see down here in this definition, f at a equals b. And we can correspond it to these points in the set G, the graph of the function. This is just saying f of a is b. And this is saying, or b1 rather, f at a equals b2. Since we said that this is a function, this implies b1 equals b2. So there's lots of ways to kind of conceptually define functions, but the unique output is the major idea. So we have the property that b1 has to be equal to b2 to define that function. So here's a random function down below, an example one. This was a really awesome example given by the mathematician, Peter, let me see if I can pronounce that. Correct me if I'm wrong. Dirichlet. That's probably wrong, but we'll review that next time I have to say that. So I'll just say Peter. He came up with this function to demonstrate functions are pretty strange and wild things. Their definitions don't have to look like this. G of x r to r, defined algebraically by g of x equals x squared. This is a real function. Every single input from the domain R will have exactly one and only one output in the codomain, also R. Notice the codomain to this function really has just two elements, 1 and 0. So this is also a reminder that the codomain is not the same as the range, where the range is the set, the collection of all possible outputs to the function. So here's our pretty bizarre looking function. It's a pretty famous example of a function. All we're going to do on this one is do a couple function evaluations and look into domain, codomain, and range. So let's think about this. It's a piece or case by case function. It's either 1 if x is rational, 0 if it's irrational. So any volunteers for what the outputs should be to either one of these?
Would f of 15 be 1?
Yeah, good call. So that one is definitely a 1, just as Jake said. And here's the reason on why f of 15 comes out to 1. 15, let's say here, just as a quick statement, this is because 15, we think of this as an integer more often than not, but you know what? You can promote this to 15 over 1. Now it's a ratio of an integer divided by an integer. So it's in an element of the set Q, which is the rational numbers. So because this is a bona fide rational number, it's kind of like how you say a square is a particular rectangle type of logic. The output is 1 because it's rational. How about for square root 2? Anyone have the value for this one?
I believe root 2 is irrational, so that would be 0.
Yeah, good call. Root 2, very different from any kind of fraction you might write down. It turns out this is impossible to write as a ratio of 2 different integers. That makes it an irrational number, like you said. And so this one will output to exactly 0. It's kind of a tricky problem when you think about it, right? It just forces us to confront very, very directly what is the difference between a rational and an irrational number. So if we give a same justification, pretty much as you just said as well, Jake, we could say that this is 0 because square root of 2 is an entry inside the real number system set minus the rational numbers. There's no way to write this as a fraction, no matter how hard you try, which means it's in the set I, irrational numbers that we define in section 2.2. That's an A there, irrational numbers. And this would be the same thing if we said f at pi, f at Euler's number E. Man, there are lots and lots of irrational numbers. Any irrational number you come up with, it'll output a 0. Now, imagine you try to plot the graph of this kind of function. That's probably going to be impossible, right? This is a really, really bizarre function altogether. Sophia says, so if the x is rational, it'll always be a 1, and irrational will always be 0, in short. Yeah, absolutely. That's the other thing that's kind of tricky about this one is we have to navigate that this is a piecewise defined function, putting 1 in the piece where we're in the set of rationals, 0 in the irrational number set, as you said. Any other questions or comments with this one? Okay, and for just a really fast rundown, the domain and the codomain are the same on this one. The first set where we define the function, this is the set of all inputs into the function f, gives us the domain, and it's R in this problem. Codomain, that's just the set that contains all possible outputs. It might be the range, but it's definitely not in this case. The codomain we indicated as R. So here's our codomain, R. But the new thing is the range. We'll define it below, but we said very loosely that the range is a set of all possible outputs. And there's only 2 outputs to this function. It's either 0 or it's a 1. So we'll say here, range of f equals 0, 1. So the range is definitely not the set R. We'll say something about this function altogether. But you know, you could redefine this function. You could say it was the function f from the real numbers into the set that contains just 0, 1. You're changing how the function is defined, but in a certain sense, you're not changing any of the values whatsoever. So it's really up to how people just decide to present the function. what codomain might seem natural. Here, 0, 1 might have been a better thought, but it's still the correct function if we go with the codomain R. Your codomain just has to contain all possible outputs. It doesn't have to be directly equal to the set of all possible outputs. So that's a kind of interesting function to start out thinking about functions and the weird and wild behavior. There's even weirder functions like the so-called Weierstrass function. A person came up with an example of a function that's continuous everywhere, differentiable nowhere, and the domain is all real numbers. Turns into some crazy fractal shape. And, honestly, this is just as bad. It's not continuous anywhere. It's got a lot of different jumps. Well, let's move on to the next topic, unless there's any questions or comments getting through this one. Okay, so nothing too serious just yet on the next topic. Here we just define formally what we mean by range. Often said or called image in linear algebra class, that might be slightly more common. The range of a function where we map from a domain A into the codomain B is going to be the set of all elements B in the codomain such that f of B maps to or outputs that B element. So in other words, we can rewrite the range as all elements Y in the codomain such that there exists at least one. We don't care about uniqueness. There could be multiple values, but there's at least one element in the domain that maps to that value. Or, said very quickly and loosely, the set of all possible outputs to your function. As a set, this is what it would look like. And the goal for these problems, let's kind of hide this one so we go one at a time, is to just state the natural domain and codomain for every one of these functions as we see them. So it kind of starts off kind of nice for a couple warm-up problems, but some of these do get kind of tricky. I have some trickier ones as we go. So let's think about these very carefully for each one. First to start, f of x is x to the power 1/2. I know we can kind of change the notation to make it feel more comfortable. Another way to rewrite it, this isn't redefining the function, but in different notation, f of x is square root x. For the natural domain on this one, what we mean by natural domain or implied domain is the largest set of numbers for which this whole thing makes sense. What can you actually put inside there? For example, this domain is not R. We're thinking of real valued functions in this textbook, unless we say we're specifically working in complex numbers, which won't happen too often. We're mostly going to be in the landscape of real valued functions. So what would you all say is the better domain for this, if it's not the set of real numbers? One thought on this, just to give a hint, is there's no harm in just looking into the graph. That was the alternative definition of a function that we were looking into. If we just plot f of x equals square root x, here's the graph. What we said the graph was this subset of A cross B that has a certain property that the input and output of the elements will give us the unique output when the input is the same. But yeah, it's really just a set of ordered pairs like we were indicating when we defined the function as a graph. But visually, we can see here, if it's not R, because we're not taking complex valued outputs, it should start directly at 0. That's the minimum input you could put into this function and get a real number output. So one way to write this domain is it would be equal to, let's start with the bracket 0, go off to infinity, and that's the implied domain for this particular function. I think that's a fine notation if you go interval notation like this. Sometimes our author also writes it this way. R greater than or equal to 0 will be a shorthand our author uses for this kind of notation. And consulting the graph again, the range is the set of all possible outputs or second coordinates, but the square root function just increases from 0 as well. Turns out the domain for this function is the same as the range as well. So when we say range, we don't mean codomain, the set of all outputs. A codomain could be R, and that would be appropriate, but range is specific. Range is all the outputs you'll ever get to the square root function, and it's also 0 to infinity. Or you could write it as R greater than or equal to 0, R non-negative as well. So that's the name of the game on every one of these problems. It gets slightly trickier as we go, but any questions with this one? Okay, here's another one to try. And this one's definitely different, right? Let's recall what this is. This was from section 2.2, and this one has the name, the greatest integer function, or the ceiling function for short. So just to practice with this one, if you took, say, g at 3.5, the output to this is going to be the smallest integer that is greater than or equal to 3.5. So g at 3.5, integers greater than or equal to that are 4, 5, 6, 7, but the smallest such integer would be a 4. So that's what a typical input and output would look like to this kind of function. Well, we could say right away to this, the domain is not restricted like the square root function. For both the ceiling function and the floor function, the domain is going to be all real numbers. But the codomain and the range is different. Sorry, go ahead.
Could we write this as from negative infinity to positive infinity, or would that be wrong?
Yeah, that would be a great way to express it. In fact, I like that. Let's kind of make the notes more parallel and go in that route. You could just say negative infinity, positive infinity, or you could use the symbol R. I'll leave that up to you. Or if you prefer just ordinary words, you could just say domain is all real numbers, and that'd be a third great equivalent way to say it. So yeah, that's a great suggestion on these, just to parallelize the notes as well. Well, how about for the range? Anyone see what the range would be for this particular function g?
Would it be integers this time?
Yeah, exactly. This time, it's really restrictive. The hint is kind of in the way it was defined, and just like Hiram said, if integers are your only possible output, fast way to say that would just be writing, well, let's kind of keep this more parallel. Let's give equivalent answers. If you gave me this set, then I would have to kind of read between the lines here and think to myself, you mean the set of all possible integers. So you know that would qualify as a set, much like the interval notation. Faster way to write this out, which doesn't require anyone to read between the lines, would just be to say z. Or you could just say verbally, all integers. That's completely fine as well. And this is just the one symbol, much like R, for the set of all integers. Really, we're just kind of going back to section 2.2 and looking into these sets from way back in the day. You know, it might not be a bad idea to kind of keep this in view as we put down some of these values. We looked at irrationals, the rationals, the real number line, which is the union of irrationals and the irrationals. But now, for the range on this function, we have just the set of integers. Those are the only possible outputs to both the ceiling function and the floor function as well. Well, that's two down. Let's try and see what's going on with the next one. But any questions at the moment? Okay. Now, this one, I have to be really careful with how I define it. If I say h of x is x times x, and that's all I said, a completely fine and valid interpretation is maybe Mike means f of x is x squared, and we're looking into that function. But I said a little bit more. That's not standard multiplication whatsoever. It's the dot product operator. So this takes us back into section 2.4. The dot product operator is defined only in the context that x itself is a vector in Rn. It didn't say which, so this is a more abstract problem as well. For this one, we would say the domain is, instead of writing down the set this time because it's getting kind of a more built-up operator, it's going to be Rn. And we can relate that back into a Cartesian cross product where Rn is going to be equal to R cross product R. And then you do this a bunch of times until you have n copies of R. So that's the domain of this one, only because we said dot product operator is operation here. Inputs to the function h then have to be vectors in Rn. And when we take the vector, we're just making it be the dot product with itself. That might feel kind of familiar as well, because we said the length of a vector x. Let's specify where x comes from. The domain is important when you just write down a random symbol. So let's say if x is in Rn, the length of x is root x dot x. So that means if we see just x dot x, that function h is outputting the length squared this time for every single vector in the domain Rn. But that kind of directs us what the codomain should be at the, excuse me, not quite the codomain. We're going for range. That directs us to what the range should be for this particular problem. Now, this is a pretty interesting mapping when you think about this. The domain is complicated, n-dimensional space, and it's implied here, maybe we should say it to be specific. It's implied that n is greater than or equal to 2 to define that dot product operator. But anyone see what the range should be for this particular problem?
Would it be Rn or R2n?
It turns out it won't be at Rn on this one. This one's one of those weird problems where we went from a pretty complicated looking space, but the space here is a lot less complex. It kind of gets simplified down to just one non-cross product type of set. Anyone happen to see what it should be?
R.
Yeah, you're pretty close to it. It turns out the codomain for this function will be R, but there's a little bit more going on. We have to actually shrink it down even further on this one. And here's the idea. When you take x dot x, it doesn't matter what that vector could be. Let's just write down a quick example. Maybe x equals 1, 3, -2, something like that. Doesn't matter which values are positive, negative. They could be all zeroed out as well if you prefer. This would be an entry in R3. So we're saying the domain is R3 this time. And if you took x dot x, you're taking the square of all the entries. It'd be 1 squared plus 3 squared plus -2 squared, because you're taking in that dot product the corresponding elements of one vector, the first one, times the corresponding elements of the other vector, the second one. but that just squares them all together. So this one's going to come out as 1 plus 9 plus 4 for 14. And you can make that smaller and smaller or larger and larger, but you can never make it negative due to the power 2 on this one. So this one goes back to a range of 0. Only way to get a 0 is if x had 0, 0, 0 for this example, off to infinity. And an equivalent way to say it is r greater than or equal to 0 if you like that symbol there. Our author does use this a lot, so it's a good one to be aware of. But again, this got kind of tricky, right? When we change the landscape of what the domain is and look into some random operator like a dot product, getting domain and range down is kind of a tricky task altogether. So we've got more tricky ones to take a look into, but any questions or thoughts on this one? Okay, the homework exercises will go through a couple scenarios just like this one. So use this as kind of a motivation and guide for some of the weirdness that can come up, but if you see one that just seems pretty weird, don't hesitate to ask about it. Come to office hours, send it to email. It could be a great question to start out class with as well. But for today's class, I think this will be a good one to end on. Then when we come back on Thursday after the Tuesday's exam, we won't have class on Tuesday since it's conceivable some people schedule their exam during class time. When we come back on Thursday, we'll start looking into onto functions, one-to-one functions, and bijections. But same question on this one. What is the domain and range? And here's a new kind of function. This is the kind of function that could be studied in a linear algebra context or a calculus 3 kind of context. But you know it fits in our context as well. It doesn't matter how crazy the domain and range gets, we can still describe it. So here, this is a function f that takes two elements, x and y. We don't have any crazy operation like the dot product operator, so it's okay to assume that these are just ordinary real numbers. If there's more going on with x and y, I have to say that some way, somehow. Like saying it's a dot product or just directly saying the element x came from Rn or some special set. So if it's written here, it's an okay assumption to say that x and y are ordinary real numbers. That then tells us what the domain should be. The domain will be equal to R2, just a ordered pair of numbers that we're plugging into the function. And we're getting a vector that looks like this. Now, if the question was, what is the codomain? That's not too bad. The codomain, it's not what we're directly asking about, but it helps us think about the problem. The codomain contains 3 components in the vector that it outputs. So that means it's R3 itself. So we're going from two-dimensional space into 3-dimensional space. So it's a pretty crazy function when you think about that. The big question, though, is what is the range of this function? I think this one is kind of the tough question for the day. If you've taken Calculus 3 and linear algebra, you probably have a good idea of what it might be. But it turns out the best way to think about this one is to go back to section 2.4. We're going into this content. Think about the operations that we did with vectors down here, like the linear combinations. We took a combination 2a minus b plus 4c, and we just cranked that out and got a value, 517. What we want to do is take this output. The range is all possible outputs. So let's take that and go backwards. In other words, take something like this and deconstruct it in terms of the x's and y's that we see. So from here, let's go and say x plus y, x minus y. We can break this down as, say, let's collect in a first vector all the x's that show up. That'll be an x from this component, and x from this component, and an x from this component. Then go plus the vector that contains just variables y. Y doesn't show up here at all, so it'll be a 0. a y on this one, and a negative y on this one. That's a comma there in the middle that got kind of out of hand. Let me fix that. So although this was a kind of a more friendly problem to look at, less abstract, we're not doing anything fundamentally different. We're just going backwards and deconstructing the sum in terms of x and y. And we want to go all the way backwards and make x and y be a scalar multiplying the vector a and b will get. So here, going backwards, undoing the scalar multiplication, we can write this as x times 1, 1, 1, plus y times the vector 0, 1, negative 1. So the domain is going to be all components x, y. Once you choose an x, y, you'll have a value that goes here, a value that goes there, and you just multiply those two vectors. This is enough to actually tell us what the range will be. The range is a plane in R3 containing 0, 0, 0. That's if you plug both 0 for x and 0 for y. You're allowed to because the domain is all ordered pairs whatsoever. So you get that output. The next interesting vectors to visualize that plane are 1, 1, and 1, and 0, 1, negative 1. So that's our range here. This time we just indicated it verbally. Let's also visualize it just to give a sense for what does that plane look like to connect the dots on this one. So let's go to, there's a cool new tool on Desmos, the 3D calculator. And we could just directly plot these values. 0, 0, 0. There it is, that one red dot. 1, 1, 1. Here's that blue dot for the second point. 0, 1, negative 1. And where did that go? There's a green point down below there. So there's 3 points, and now you have to imagine the plane that contains all 3. And it has an equation, it turns out. This is where it goes kind of beyond the scope of the class, but if you're curious to visualize it, it's negative 2x plus y plus z equals 0. So there's our plane. Again, this is a pretty interesting function to think about. It has R2 as its domain. It outputs any point on this purple plane, which does indeed contain the origin 0, 0, 0, and those other 2 points we generated. So there's our there's our range on this one. Again, this one was just to show what can happen when you're talking about domain and range for these kind of problems. Not the best kind of problem for, say, an exam setting whatsoever, but a good one to think about the wild landscape of what could a function even be in the first place. And that's a pretty interesting function in its own right. Any questions at all, folks, about running through this one? Okay, I think this will be a good stopping point for us. We're kind of out of time. If you're curious on how I got that equation, negative 2x plus y plus z equals 0, let me know and I'll be happy to post the notes on that as just an extra, kind of like a comment on the Canvas page, maybe just down below over 2.5. So if you have any questions while you're working 2.5, maybe probably after you take exam 1 would be a good strategy. Focus on 2, 2, 2, 3, 2, 4, take exam 1. And then if you have any questions as you start off this section, we're about halfway through it. Don't hesitate to ask. I think domain and range are pretty tricky problems. I'm happy to take a look at your work if you have any questions on them. But have a great afternoon, folks, and a great weekend. If any questions come up whatsoever while you're studying, please don't hesitate to ask about it. Yeah, I'll be happy to do that, Mateo. Let me make that a note. And I'll make sure I get that posted under the section 2.5 notes.
Hey, I just
Fine.
wanted to make sure you knew I put my homework 2.3 on the back of 2.2.
Oh, gotcha. I'll make sure that I make sure to find it that way. Sorry, what was the
Yeah.
name?
Hiram.
Okay, gotcha. So
I just
2
noticed
point-
it was marked as missing, so.
Oh, gotcha. Sorry about that. 2.3 attached to 2.2. Yeah, I'll make sure to double check that and give the credit for that problem. Sorry about that, or that section.
Yeah, it's fine. Thanks.
Yep, have a good one. Well, take
Thank
care,
you.
folks. And again, if any questions come up, don't hesitate to reach out. I'll be happy to help. Take care.